Welcome to Everyday Mathematics. Today we are on the MIT Integration B Qualifying Exam 2010. We'll look at the first 10 problems. Problem number 1 happened to be definite integral from x equals to 0 to x equals to pi over 2 of sine x times sine 2x times sine 3x. So this is a very interesting problem, and we're going to see how to solve it. So the first thing I would do is just express some few identities, and that is cosine of A plus B is equals to cosine of A cosine of B minus sine of A times sine of B, and cosine of A minus B is equals to cosine of A times cosine of B plus sine A times sine B. So when we add this, actually we want to subtract it. So if we subtract going upwards, we'll have 2 sine A sine B is equals to cosine A minus cosine B minus cosine A plus B, and this is 0. Okay, such that sine of A times sine of B is equals to half of cosine of A minus B minus cosine of A plus B. So this is a good identity that we would like to use, right? So that when we go up here, we may choose to maybe attack that part and see that our problem becomes integral from x equals to 0 to x equals to sine to pi over 2 rather of half cosine of, if this is our A and this is our B, then we have 2x minus x minus cosine of 2x plus x close bracket sine of 3x, and that is where our problem reaches. So since our problem has gotten us to integral from 0 to pi over 2 of half bracket cosine of 2x minus x, we have cosine x minus cosine of 2x plus x is 3x, then we have sine 3x. So this is, we can pull this half out. We have half 0 pi over 2, and if we multiply that and that, we have cosine of x sine of 3x minus cosine of 3x sine of 3x. Okay, now I don't want to go so much in deriving the identity that we need here, but I will say if we have sine of A cosine of B, that is the same as a half of sine of a plus b plus sine of a minus b. Okay, so that's identity number 1 that we'll use. And then for this, we could say sine of 2a is equals to twice sine a cosine a. So that's the second identity. And so for this here, if we shall take this to be a and this to be b, we'll now have the integral as half 0 pi over 2 a half sine of a plus b will be 3x plus x is equals to 4x plus sine of a, that is 3x minus x is 2x. And then for this part here, we'll have this going down here as half. We'll have minus a half sine of 6x. Okay. And so we can pull this half and this half out. And we therefore have a quarter, integral from 0 to pi over 2 of sine of 4x plus sine of 2x minus sine of 6x. So this becomes a quarter, and we do have negative a quarter. Integrating this, negative a quarter cosine of 4x minus negative half cosine of 2x. And then we have positive, because we have a negative here, 1 over 6 cosine of 6 cxx, 0 pi over 2. Okay, so this becomes a quarter negative cosine of, if we substitute pi over 2 in there, we have cosine of 2 pi plus, because we have minus minus, a quarter cosine of 0. And then we'll have, let's just put plus here and take the negative in. So we have negative cosine of pi plus a half cosine of 0, close bracket, plus 1 over 6 cosine of 3 pi minus cosine of 0. So this goes to positive 1, this goes to positive 1, and because this is opposite to this, this and that would cancel, and this goes to negative 1, okay, and this to positive 1, and since this reverses the sign here, so we have positive half plus a half, we have 1 here. And here, since we have negative 1, and then we do have positive 1 here, so negative 1 minus 1. So rather, we now have a quarter, 0 plus 1, and then we have twice of that, negative. So which will bring us to 1 minus, in other words, a quarter times 2/3 of 1. We have 2, so is equals to 1/6. And that is the answer. And so our integral, if we may emphasize our integral from 0 to pi over 2 of sine of x times sine of 2x times sine of 3x equals to 1/6. And that's the answer. So now problem number 2. Again, a definite integral from x equals 0 to x equals to pi over 2 of the cube of sine 2x times cosine of x. And this is how we may be able to solve it. So the first thing I would do is just use the identity that we expressed previously, that the sine of 2a is equals to twice sine a cosine of a. So this is an interesting identity that we'll use to re-express that expression there. So we have 0 to pi over 2 bracket twice sine of x times cosine of x cube times cosine of x, which is equals to 0 to pi over 2. 2 cube is 8 sine cosine cube x times cosine of x. Okay, so essentially what we do have here now is we can pull 8 out, so we have 8, 0 pi over 2 sine cube of x cosine to the power 4 of x. And we can do something. We can do some substitution here. Let's re-express this problem a little bit differently, and then we see how we can substitute for that. So we had our problem come to that. Sine of 3x cosine. We can re-express this as 8 sine of x sine square of x cosine 4. So we want to express everything in terms of cosine. I will keep this, and then I will express this. This sine squared x is the same as 1 minus cosine square of x. And so if we say let u be equal to cosine of x, then that means that du dx is equal to negative sine of x. And so du negative can be used to substitute for sine x dx. Very important. And as x, when x equals to 0, u equals to so cosine of 0 is going to be equal to 1, and when x equals to pi over 2, u equals to 0. So those are for these limits. And so our problem that is as shown here, we can see that sine x dx is the same as negative du. This is u squared, this is u to the fourth, this is 1, and this is 0. So we have 8 in place of 0. We have 1 in place of pi over 2. We have 0. And then we have 1 minus u squared, u to the power 4, and then negative du in place of this times this. Okay, and so we can reverse the limits based on this negative sign. So we have 8, 0 to 1, 1 minus u squared, u to the fourth du, which is equals to 8, 0 to 1, and we have u to the fourth minus u to the sixth du, which is 8 u to the power 5 over 5 minus u to the power 7 over 7, 0, 1. Okay, so since we have 8 u5 over 5, u7 over 7, 0, 1, then we have 8 1 over 5 minus 0 over 5 minus 1 over 7 minus 0 over 7. So which is 8, a fifth minus a seventh, which is 8, 35, 7 minus 5, which is 8 times 2 over 35, which is 16 over 35. And therefore, if we can emphasize our final solution, we'll say the definite integral from 0 to pi over 2 of sine of 2x to the power 3 cosine of x is equals to 16 over 35. And that's the answer. Okay. So on to problem number 3, which is an indefinite integral of the square of x plus 1 times the cube root of x minus 1. So how may we be able to solve this? My strategy here would be to substitute for x minus 1. And how I would do that, I would say let u be equal to x minus 1 such that du dx is equals to 1, and therefore du would be equal to dx, right? So we have that as a change of variable, and therefore x plus 1 would be equal to u plus 2, right? And therefore our integral now becomes integral of u plus 2 squared, and then this becomes u to the power a third du. And so we could expand that out, and we see that u plus 2 squared is the same as u squared plus 4u plus 4 times u to the third du. And that means that we have u 2 plus a third we're multiplying across by that, plus 4u, 1 plus a third, plus 4u, which is equals now to u. And so this becomes 7 over 3 plus 4u, 4 over 3 plus 4u a third. Okay, so since our integral now has come to u, 7 over 3 plus 4u, 4 over 3 plus 4u. This can now be integrated to adding 1, so we have 3 over 10 u, 10 to the 2 over 10 over 3 plus 4 times 3 over 4 u, rather we made a mistake there. So it's 3 over 7, 7 over 3 plus 4, 3 over 4, u 4 over 3 plus c. So this becomes 3 over 10, u 10 over 3 plus 12 over 7, u 7 over 3 plus 3 u 4 over 3 plus c. But we said u equals to x minus 1, therefore our integral becomes 3 over 10 x minus 1 10 over 3 plus 12 over 7 x minus 1 to the power 7 over 3 plus 3 x minus 1 4 over 3 plus c. We can do, since our problem is this, plus 12 over 7 x minus 1 7 over 3 plus 3 x minus 1 4 over plus c. We can pull this out so that we have 3 x minus 1 4 over 3, and we have 1 over 10 x minus 1, and we have 6 over 2, which is squared, and then we have 4 over 7, 7 over 3 minus 4 over 3 is 3 over 3, so which is 1 plus 1 plus c. So to now emphasize our problem, we say our indefinite integral of x plus 1 squared x minus 1 power third is equal to 3 x minus 1 4 over 3 1 over 10 x minus 1 squared plus 4 over 7 x minus 1 plus 1 plus the integration constant, and that is the answer. Okay, so on to problem number 4, which is the indefinite integral of x times the natural logarithm of 1 plus 1 over x. Okay, so I guess this is the same as x times the natural logarithm of x plus 1 over x, right? And using the rules of logs, we can also express this is the same as x log of x plus 1 minus x log of x, right? And we can re-express this a little bit differently. We can say this is the same as log of x plus 1 times the derivative of a half x squared x minus integral of log of x times the derivative of a half x squared. Now we can use integration by parts, where if you have a product of a function v and the derivative of a function u, when you integrate that, then that's the same as uv minus u dv dx, right? So that's what we can use. And so since we have an integral where we have log of x plus 1 derivative of a half x squared minus log of x derivative of a half x squared, we see that this is our u, this is our u, this is our v, this is our v. So our problem now becomes a half x squared log of x plus 1 minus, we can pull half out, we have x squared times the derivative of log of x plus 1 minus, we have a half x squared log of x minus minus, which becomes a plus, half of integral of x squared derivative of log of x. Okay, so this becomes a half x squared log of x plus 1 minus a half, and this becomes integral of x squared over x plus 1 minus a half x squared log of x plus a half integral of x squared divided by x. So this and this can be brought together so that we have half x squared log of x plus 1 over x minus a half integral of x squared over x plus 1 plus a half integral of x. Okay, this becomes x squared log of x plus 1 over x minus a half, and then we have x minus 1 plus 1 over x. So just long division here, nothing very special about that, plus a half x dx. So which is a half x squared log of x plus 1 over x minus, we have a half x squared, this and this interact, so we have plus a half x, and then we have minus a half log of x plus 1, and then this is the same as plus a half squared. And you see that this and that would cancel, we have a c there, and so the solution becomes half x squared log of x plus 1 over x plus a half x minus a half log of x plus 1 plus the integration constant. So now we can summarize our problem by emphasizing where our problem started and saying that the indefinite integral of x, natural logarithm of 1 plus 1 over x, is equal to I have x squared log of 1 plus 1 over x, because it's x squared, x plus 1 over x, and then we have a half x, and then we have minus a half log of x plus 1 plus the integration constant. And that, ladies and gentlemen, is our solution. To problem number 5, which is the definite integral from x equals to 0 to x equals to 1 of the square of the natural log of the square of the sine of natural logarithm of x. So the obvious thing here for one to do is to substitute for the natural logarithm of x. And what we do is you'd say let u be equal to the natural logarithm of x, meaning that the derivative of x of u with respect to x is 1 over x, and so x du would be equal to dx. Now from here, x is equals to e to the power u, and therefore e to the u du would be equal to dx. When x equals to 0, u would tend to negative infinity. When x equals to 1, u would be equals to 0. Therefore, in the u domain, our integral would start from negative infinity to 0 over sine squared of u times eu. And so this is our problem. The important thing to note here as well is we could remove the negative sign, and I would go about doing that. So since our problem is that this is obviously an even function, so both in the negative and the positive direction it would still remain the same. So if we say, let's say, okay, let's just do this and say let u be equal to negative y, such that du would be that. And that means that we have e and this remains, so this negative sign propagates outwards, and we have the square of that would just remain. So, and we can use this negative sign to reverse the sign there, and this is what our integral now has become. So since we have now 0, infinity, this is 0, and there should be a half somewhere. So pulling it out, we have this one here is simple because this is the same as a half negative, and we'll keep this for now. To that. Okay, and so now that we are at this point where we have and then it's easy to see that here we have half limit as y tends to infinity of negative minus limit as y tends to infinity of negative rather 0 here minus a half. So this tends to 0 and this tends to negative 1. So we have a half so we want to make this I such that we say that I is equal to a half 0 infinity equals 2y. We're going to use integration by parts because this is very cyclical. So we have, let me rewrite that. So this is equals 2y derivative here of negative. So since I, we've said is a half of 0 equals 2y derivative, you can use integration by parts. Right? If we have a product of a derivative of function u and function v, if you integrate that, then this is what you get. So our I therefore is equals to a half negative e y equals, and then since we have a negative and this negative here, we have a plus of a half 0 times a derivative of cosine of 2y. Okay, so this limit as y tends to infinity, this goes to 0, and so we have a half 0 minus 1. Okay, plus a half 0. This is negative 2 sine 2y. Okay, so we have a half minus, we brought this minus out here, 0, infinity to y. Since I is equals to a half minus 0 to infinity, we can re-express this as sine 2y derivative again integration by parts, a half infinity plus the derivative of sine 2y close bracket. So this is, so here both at lower and upper limits we have 0, so we're just going to have half, and this minus would interact, this plus would interact, and so we have 0 infinity 2 cosine of 2y. So I is equals to a half, and we're back to e to the y cosine 2y. And that's where now we can begin to play around with things a little bit. Since we see that we say that I is equals to a half minus twice 0, and originally we had said that I is a half right. Therefore I is equals to a half minus twice I, and therefore I is equals to a half minus 4i, meaning that 5i is equals to a half, and right. Now we have to go back and look at our initial. So since our initial problem was a half minus I, and yet and since I is equals to 1 over 10, therefore the integral that we had, which is from 0 to 1 of the square of sine of natural logarithm of x, is equals to a half minus 1 over 10, which is 5 minus 1, which is 4 over 10, therefore this is 2 over 5. So to just emphasize our problem, I'll write it in yellow. Is equals to that. Okay. So problem number 6, which is indefinite integral of 1 over 1 plus 3 times e to the x. So what we can do here is let's divide both the denominator and the numerator with e to the x, so that we have e to the power negative x, and we have e to the power negative x plus 3 in the denominator, which means that the numerator is essentially negative of e to the x plus 3 over e to the x plus 3. And when you have such an integration problem, then in a scenario where, let's say, the numerator is a derivative of the denominator function x, this is the same as, right, plus c. Therefore, what this means for us is that since our problem is as follows, this becomes so. Just to emphasize, our integral of 1 plus 3x is the same as and that is the answer. So problem number 7 is the definite integral from x equals to pi over 4 to x equals to pi over 3 of 1 over the cube of sine x times the fifth power of cosine x. So this looks quite intricate, but it's going to take some time for us to solve it. So just relax and we'll be able to do it. Okay, let's see this. So this is the same as one squared, right? There's a reason I'm doing that. And we know that sine squared of x plus cosine squared of x equals to 1. So using this identity, we can say that our problem is the same as okay, which is equal to okay. So term by term, if we divide through, we get okay. Let's do something like that. plus cosine, that's we can yeah, let's leave cosine x there so that we have sine. Okay, so the interesting thing is we can see this as our target of substitution. This. And how do we go about that? We can say for the very first problem there, we say let u be equal to cosine x such that du is equal to negative sine x dx. Okay. Let's rewrite. Let's rewrite this clearly so that it's easy to see. So we have um, okay. So here we are saying let u be equal to cosine of x such that du dx is equal to sine x, and so du is equal to negative nx dx. And then when x is equal to pi over 4, u is equal to root 2 over 2. When x equals to pi over 3, u is equal to a half. And here we can say let y be equal to cosine of x as well. Probably, I think the same applies here, so we don't need to really do that. I would probably just spend time on the next here where I can say let y be equal to sine x dy dx is equal to cosine of x, dy is equal to cos of x dx. Then when x equals to pi over 4, y is equals to root 2 over 2. When x equals to pi over 3, y equals to root 3 over 2. Such that here our problem becomes root 2 over 2 a half. This part here becomes negative du over u to the 5. Okay, plus 2. We have root 2 over 2 a half. This becomes negative du over 1 minus u squared u cube plus root 2 over 2 root 3 over 2, and then we have u cube 1 minus u squared. Okay, so that's interesting. Definitely we're making progress there. So we have our problem, negative from root 2 over 2 to a half du u to the fifth minus 2 root 2 over 2 to a half u3 plus root 2 over 2 root 3 over 2. Right. So this one here is straightforward. We just want to play around with that partial fraction so that we know what we're dealing with. So when we have 1 over 1 minus u squared u to the 3, that's the same as 1 u 1 plus u to the 3. We can pull u3 out so that we have that, and this is the same as a half of 1 over u plus, and we pull that out and we take 1 u out in, we have that, we can, it's the same as u plus minus 1. We can add this and that so that we have send one of the u in, so we have u squared we have 2u squared plus 1 over u plus 1 this and that would cancel, so we have so send this u in, we have half okay. So since we have a half, the half 2 plus 1 over u this is a half plus 2 over u plus 1. Okay, so therefore our problem that we had is so these two and these two go, and our problem is now negative integral from root 2 over 2 to a half of 1 over u to the 5 du minus integral from root 2 over 2 to a half of 2 over u to the 3 plus 2 over u plus 1 over 1 minus u minus 1 over 1 plus u du plus half the integral from root 2 to over 2 to root 3 over 2 of the same 2u3 2u plus 1 over 1 minus u minus 1 over 1 plus u. So integrating this, we get 1, actually, yes, a quarter of u the power negative 4 from root 2 over 2 to a half. And then the second part we have so twice times a half, actually negative a half of u negative 2, so that and that cancel. And then here we have twice natural logarithm of u plus, actually this becomes negative, natural logarithm of 1 minus u minus log of 1 plus u from root 2 over 2 to a half plus a half negative 2 plus twice log u minus log 1 u log 1 plus u from root 2 to root 3 over 2. So we can consolidate this and this one by taking these two up so that it's u squared, and then using the rules of logarithm where this becomes u squared divided by 1 over u times 1 plus u, which is simple. So let's just express it in a more compact fashion. So we have a quarter u to the negative 4 root 2 over 2, a half minus u to the squared plus natural logarithm of u squared over 1. This times this is a difference of 2 squares, so we have 1 minus u squared in bracket. Root 2, 1 over 2 plus now a half negative u to the minus 2 plus log u squared, 1 minus u squared, root 2 to root 3 over 2. So we're making progress. So we've come to the point where we have a quarter u to the negative 4 from root 2 over 2 to a half minus we do have u to the negative 2 plus log of u squared over 1 minus u squared from root 2 over 2 to a half plus a half negative u squared plus log of u squared over 1 minus u squared root 2 over 2 root 3 over 2. So this becomes, obviously, we can pull a quarter out and we have 1 over a half to the 4th minus 1 over root 2 over 2 to the 4th minus negative 1 over a half squared plus log of a half squared over 1 minus a half squared minus minus, or minus, let's put a big bracket here. So we have minus 1 over root 2 over 2 squared plus log of root 2 over 2 squared minus 1 over root 2 squared. Close bracket, and then the curly brackets. And then we have plus a half. We're now on this part here, which is bracket 1 over root 3 over 2 squared plus the log of root 3 over 2 squared minus 1 minus root 3 over 2 squared, close bracket, minus negative 1 over root 2 over 2 squared plus log of root 2 over 2 squared over 1 minus root 2 over 2 squared, and you close the bracket. So for this part here we have a quarter, and this is 2 to the 4th, which is 16, and this is 2 the 4th over 2 squared, which becomes 16 over 4. So this is this, and then minus, let's delete this, we have negative 4 plus log of a quarter over 1 minus a quarter. Okay, then we have negative 4 over 2, yes, plus log of root 2 squared is 2, 4 squared is 4, 2 over 4 is a half, so we have a half over 1 minus a half. And then we have plus a half we have negative 2, actually 4 over 3 plus log of 3/4 over 1 minus 3 over 4, and then minus negative 4 over 2 plus log of 1/2 over 1 minus 1/2. So the quickest thing to see here is this here is going to be 1/2 over 1/2, which is 1, and the same thing here. So this becomes log of 1 is 0. This also becomes 0. So here we have 1/4 in bracket 16 minus 4 minus negative 4 plus log of 1/4 over 3/4 is going to be 1 over 3. Okay, then minus minus 2, so it becomes plus 2, and then plus 1/2 negative 4 over 3 plus natural logarithm here of 3/4 over 1/4, so that's going to be 3, and then plus 2. Okay, so this is 12 over 4 is going to be 3 minus negative 4 plus 2, we're going to have negative 2 plus log, actually a third is going to be, we're going to put minus there, so negative 1/3. This is negative 3 to the power negative 1, and negative 1 comes here, so we have negative log 3, and we can close that, so we have 1/2 negative 4 plus 2, so that is 6, positive 6 plus, so this is negative 2 over 3 plus log 3, and so close bracket. Okay, we're making progress here. We say that our problem is now 3 minus negative 2 minus log 3 plus 1/2 negative 2, actually positive 2 over 3 plus log of 3. This becomes 3 plus 2, this and that interact, plus 1/3, this and that, and then we have this and that, we have log 3 plus 1/2 log 3. Okay, we are progressing. So this is 16 over 3, because this is 5. 5 times 3 is 15, plus 1, we get 16 over 3, plus 3 over 2 log 3. And so that actually becomes the solution to our problem, which was, if we can now emphasize our initial problem, which is a definite integral from pi over 4 to pi over 3 or 1 over sine cube of x, and then cosine to the 5 of x is equal to 16 over 3 plus 3 over 2 log 3. And now, ladies and gentlemen, what's the much awaited answer? So problem number 8 is the definite integral from x equals to 1 to x tends to infinity of 1 over x times the square root of x to the 4th minus 1. So we can rewrite this problem in such a way. We can say, okay, let's bring x to the power 3 up so that we have x to the 4th below times the square root of x minus 1. And we could try and substitute for that bit, and we can say let u be equal to the square root of x to the 4th minus 1, such that u squared is equal to x to the 4th minus 1, and so 2u du dx would be equal to 4x to the 3, such that 2 over 4 u du would be equal to x3 dx. And this is 1, so this is a half, right? So using that, it's very easy to see this part here is very similar to this part. So let's first of all deal with the limits. When x equals to 1 rather, when x equals to 1, u would be equal to 0 as x tends to infinity, u also tends to infinity. So in the u domain, we can clearly see that for this, we have 0. For this, we have infinity. And then for this part here, we have half, not a quarter, but rather half, sorry. Half u du, and then from here we can see that u squared plus 1 equals to x to the 4th. So in place of this we have u squared plus 1, and then in place of this we have u, and these u's cancel, so we can pull this constant out, and we have half integral from 0 infinity of 1 over u squared plus 1. Now 1 over u squared plus 1, that's a very famous integral, so we have something like that, arctangent of u, 0 to infinity. Okay, so we have half arctangent of u, 0 to infinity. Now, since the arctangent of u is continuous in this domain, we don't have to really overthink it. We have limit as u tends to infinity of the arctangent of u minus limit as u tends to 0 arctangent of u, right? So this is half. We have pi over 2 here minus 0, which is pi over 4. So to emphasize our problem and solution, we can now say that the problem that was integral from 1 to x tending to infinity of 1 over x times the square root of x to the 4th minus 1 is equal to pi over 4. And that, ladies and gentlemen, is the answer. Problem number 9 is the indefinite integral of 1 over x times x to the 5th plus 1. So we're going to use the same approach we used for problem number 8, and that is we first of all introduce x to the 4th up, such that we have x to the fifth down, and then we have x to the fifth plus 1. Okay, and then we could as well just say let u be equal to x to the fifth plus 1, such that du dx is 5x to the fourth, and that means a fifth du would be used to substitute for x to the fourth dx. And very quickly we see this is same as that. So we have in the numerator, we have a fifth in the u domain, du, over, and from here we see that x to the fifth is the same as u minus 1, right? So we have x to the fifth as u minus 1, and then x x to the fifth is u. Well, we can pull that a fifth out, and we have 1 over u minus 1 u du. And we can now express that as partial fraction, and that is a fifth 1 over u minus 1 minus 1 over u. And so we get, let's delete that 5, I meant to write a fifth there. So we have now f1 over 5. Integrating this part, we get natural logarithm of u minus 1 minus 1 over fifth natural logarithm of u plus the integration constant. Okay? And so we say our problem now has gotten us to we can combine that into u minus 1 over u using the rules of logarithm, common constant comes out. When you have log differences of logs, it means you divide whatever is under the log sign. Okay, so what is u? What is u? We said u was equal to x to the fifth plus 1, and therefore u minus 1 is equal to x to the fifth. So our problem becomes a fifth log of x to the fifth over x to the fifth plus 1 plus the integration constant. Now, to emphasize whatever problem we had, we say the indefinite integral of 1 over x times x to the fifth plus 1 is equals to a fifth of the natural logarithm of x to the 5 over x to the 5 plus 1 plus the integration constant. And that is the answer, ladies and gentlemen. So problem number 10 is the definite integral from x equals to 0 to x equals to pi over 4 of the square root of tangent of x. Now this problem is a little bit more involved, so we'll just have to be patient as we solve it. The first thing is, as is the case with other problems, we try to substitute away the complicated part. So we'll say let u be equal to the square root of tangent of x. And what does that mean? It means that u squared is equal to tangent of x, meaning that 2u du dx is equals to this derivative of tangent of x is secant squared of x. Okay, and that would mean that 2u over secant squared of x du could be used to substitute for dx, but we know secant squared of x is the same as tangent squared x plus 1, and that means that 2u and since this is u squared, which is u to the fourth plus 1. Okay, so this is the mountain that we need to first of all climb, and then when x equals to 0, u equals to square root of tangent of x, so u would be equal to 0, and x equals to pi over 4. Tangent of pi over 4 is 1, so square root of 1 would be, so u would be equal to 1. Therefore, in the u domain, the problem becomes the integral from 0 to 1 of the square root of tangent of x is u, and we said dx is the same as 2u over u to the fourth over 1 du, which means we have twice the integral from 0 to 1 of u squared over u to the fourth du. Now, what's key to know is 1 plus u squared is the same as 1 plus 2u squared plus u to the fourth, right? Such that this and that, 1 plus u squared minus 2u squared is equals to 1 plus u to the fourth. Okay, this is here. Then we can now re-express this as the square root of 2u squared is equals to, right. But we know that a squared minus b squared is the same as a minus b, a plus b, right? Using this, therefore, we have 1 plus u squared minus root 2u, 1 plus u squared plus root 2u is equals to 1 plus u to the fourth. Very important relation. So in other words, so our problem, which is twice the integral from 0 to 1 of u squared over 1 plus u to the fourth, can now be expressed as twice the integral from 0 to 1 of u squared of 1 plus u squared minus root 2u times 1 plus u squared plus root 2u. And so if we play around and we bring u there so that we have u over this problem becomes twice integral from 0 to 1 of u, and here we have this, if we split that such that we have 1 over 1 plus u squared minus root 2u minus 1 over 1 plus u squared plus root 2 of u, then we're going to remain with twice of square root up, so we have to divide that with that. And these twos go, so eventually we have 1 over root 2 integral from 0 to 1 of u over 1 plus u squared minus root 2u minus u over 1 plus u squared plus root 2 of u. Okay, so that's fascinating. So since our problem has come to 1 over root 2, 0, 1, u over 1 plus u squared minus root 2u minus u over 1 plus u squared plus root 2u. To express this such that the numerator is the derivative of the denominator, we can do as follows. We can introduce half there so that we have, first of all, twice of u in the numerator. And you see this part here is the derivative of this. What about this part here? So we can now go ahead and say, okay, let's introduce a phantom root 2 at the top. We do have to compensate for that. And how do we do it? Since this is a minus, we have to add. And we made a small mistake here. That's a minus. And then since this and this is a minus as well, we have to add here as well. Okay, so we're making progress. So since our problem now is 1 over 2u minus root 2u over 1 plus u squared minus root 2u minus 2u plus root 2. It's not a u here, we made a mistake here. That is just 1 plus u squared plus root 2 of u du plus root 2, 0, 1, root 2 over 1 plus u squared minus root 2u plus that root 2 over 1 plus u squared. So we can express this here as a 0 to 1, the derivative of 1 plus u squared minus root 2 of u over 1 plus u squared minus root 2 of u minus the derivative with respect to u of 1 squared plus root 2 of u over 1 plus u squared plus 2 of u. And then we can just combine the next integral, which is 1 over 2 root 2, 0, 1, root 2 plus squared minus root 2 of u plus root 2 over 1 plus squared 2 of u. So here the first bit we can say, okay, that is simple. So we have log of 1 plus u squared minus root 2 of u minus log of 1 plus u squared plus root 2 of u, 0 to 1. And then we can express this as and we can bring this root 2 here out, 0, 1, and we have 1 over u minus root 2 over 2 squared minus a half plus a half plus one over u plus root 2 over 2 squared minus a half plus, 1 here, plus 1. This one and this one. And this part here is the same as u minus root 2 over 2 squared minus a half. So this is what we've brought here. Same here as well. We can combine this part here. So since our problem now was in this, our solution was in this format, we can combine these two expressions. So we have 2 root 2 log of 1 plus u squared minus root 2u over 1 plus u squared plus root 2u. Okay, then this and that would cancel. Then we have, if we multiplied both the numerator and denominator by 2, right? So we have 2, and we have 2u minus root 2 over 2 squared 2 over 2 plus 2 over 2. So this is simple because we have limit as u tends to 1 of log of 1 plus u squared minus 2u over 1 plus u squared plus root 2u minus limit as u tends to 0 log of 1 plus u squared minus root 2u over 1 plus u squared plus root 2u. Right? And then we have half. We can separate this integral into two separate integrals. 2, and we can tack this root 2 under the square. So we have root 2u minus 2 over 2 squared plus 1 u plus a half 2 root 2 plus 2 over 2 squared plus 2 over 2. Okay, this is 1 rather, so no, du. So we can see this here is going to be log of 1, actually 1 plus 1 minus root 2 over 1 plus 1 plus root 2 minus log of 1 over 1, which is 0, which is equals to this 2 and 2 cancel, this 2 and 2 cancel, plus here, so rather 0, 1 over root 2u minus 1 squared plus 1 du here plus 0, 1 over root 2u plus 1 squared plus 1. Okay, so our problem becomes 2 root 2 over 1 log of 2 minus root 2 over 2 plus root 2 plus integral 0 to 1 or 1 over root 2u minus 1 squared plus 1 du plus 0, 1 over root 2u plus 1 squared plus 1. So we can rationalize things here. This is okay. U minus 1 squared plus 1. Log, this is the same as 4 minus 2 root 2 plus 2 over 4 minus 2 plus 0, 1 over root 2u minus 1 squared plus 1. We're just still carrying these things a little bit along, but just trust me, we're going to reduce them. So this becomes log of 6 minus, actually this is 4 rather, 4 root 2 over 2, 1, 3, 2 plus 0, 1. Okay, so this can be expressed as 1 over 2 root 2 log of 3, 2 root 2 plus these two integrals. So this is 1 minus root 2 squared so to factor away that a half, we have okay. And so we have 1 over root 2 log of 1 minus root 2 plus these two integrals, which we are shortly going to now solve. If we say let y be equals to root 2u minus 1, this means dy du is equals to root 2, which means dy root 2 equals to du. Very important. When u equals to 0, y is equals to root 2, when u is equals to not root 2 rather, sorry, y is equals to -1. That was important. Y u equals to 1, y is equals to root 2 minus 1. And we could do the same substitution here so that our solution now becomes something of this sort. So we have okay. Root 2 plus 1. So this is, apologies, this is getting a little bit windy. We can pull this out and we have arctangent over root 2 minus 1 minus arctangent of -1 plus, okay, root 2 plus 1 minus. So on this specific value, if we are to plot arctangent is that function, and this is obviously pi over 2. But if there is an a value a there, and then there's a -a, we realize that this value here at -a is opposite in sign with the value at +a, right? And so for -1, this sign is going to come out there, so that we have 1 over root 2 log of 1 minus root 2 plus 1 over root 2. Let's combine everything. We have root 2 minus 1 plus arctangent of 1 now plus arctangent of root 2 minus 1 minus plus 1 rather, arctangent of +1. And this and that cancel. So we have 1 root 2 log of 1 minus root 2 plus root 2 arctangent of root 2 minus 1 plus arctangent of root 2 plus 1. So how do we simplify this? Imagine we call this A and this B. So if we have arctangent of A minus B plus arctangent of A plus B, and this is x and this is y, then it means that x plus y is equals to arctangent of A minus B plus arctangent of A plus B, and the tangent of x plus y is equals to the tangent of arctangent of A minus B plus arctangent of A plus B. And if we are to use the identity tangent of A plus B, that is the same as tangent of A plus tangent of small b minus 1 over 1 minus tangent of A tangent of B. Okay, so using this identity, we now have tangent of x plus y is equals to tangent of arctangent of A minus B plus tangent of arctangent of A plus B over 1 minus tangent of arctangent of A minus B times tangent of arctangent of A plus B. Okay, therefore tangent of x plus y is equals to A minus B plus A plus B over 1 minus A minus B times A plus B, right? This and this cancel, so we have 2A over 1 minus A squared minus B squared. So if A is equals to root 2 and B is equals to 1, then we see that tangent of x plus y is equals to 2 root 2 over 1 minus root 2 squared is 2 minus 1. And therefore, since this is 2 root 2 over 1 minus 1, and therefore tangent x plus y tends to infinity. So therefore, x plus y is equals to a limit as u tends to infinity of the arctangent of u, which is pi over 2. So the final answer becomes now, so we had 1 over root 2 log 1 minus 2, and so this answer actually is not correct, and I'll mention that in a minute. Plus that, since this is negative, in the strictest sense, since we derive this from which is actually, instead of 1 minus root 2, we could just say root 2 minus 1 squared. So this becomes log 1 over root 2 over root 2 minus 1. And so in the strictest sense, our answer, sum up everything, the integration from 0 to pi over 4 of the square root of tangent of x is equal to pi over 2 root 2 plus 1 over root 2, the natural logarithm of root 2 minus 1, or is equals to pi over root 2 minus 1 over root 2, the natural logarithm of 1 plus root 2. That there is the final answer, ladies and gentlemen. So it was an absolute pleasure hanging out with all of you. If you are not subscribed to our channel and you're interested in what we're doing, please, we do encourage you to continue subscribing, to subscribe to our channel, and please leave a comment or question if you may have, and we'll get back to you. So without much ado, have a blessed day ahead, and yeah, see you next.